Okay guys, so I'm making this video to go over the examples that I didn't get to go over in class today in lecture. The lecture I'm talking about is the fifth lecture of the class, which is probability day 3. And the very last problem we did was example 4. We're working on conditional probabilities. And so we're going to continue with that now with example 5. So let's take a look at that one. Now one thing about example 5 that's different than in example 4 is in example 4 we were drawing one ball out of this bag. And this time we're drawing more than one. So the experiment is we draw two balls from a bag, one by one with replacement. We're going to do a without replacement problem soon, but this one is with replacement. What does that mean? That means I draw the first one, put it back in, and then draw the second one. Now I know this part over here where I label what the events are might be a little confusing, but it's not a big deal. Basically what I'm asking you is to find, when we look at this first example here, I'm asking you to find what's the probability of the second one. So the number down here is telling you which time you're drawing. What's the probability the second ball you draw is red, given that the first one is red? And then same thing for the other one. So this would be the second ball is green, given the first ball you draw is red. Okay, so the number underneath the letter just tells you which draw you're on. Is it the first draw or the second draw? When you're drawing from a bag once versus more than once, and you're trying to find conditional probabilities, I want you to think of them way differently. In class, we said that when you draw once, I said, think about it like this. Imagine I draw the ball out of the bag. I show you, but I don't look at it, and you give me information. But this time, since we're drawing more than once, I want you to think about it a little differently. So think about it like this. I want you to imagine that this has occurred. The event after the vertical line has occurred. And I'm about to draw the second time. So I've drawn the first one, and I'm about to draw for the second time. So what's happened the first time? I've drawn a red one. Okay, that's what it means. So the first ball I drew was red. And then we're about to draw the second time, but when you go to draw the second time, you have to think, how does the sample space change? And the answer is it doesn't change. Sample space doesn't change. Let me write that down. Sample space doesn't change. Why? Because after you draw the first ball, it's red. You put it back in before you draw again. So when you're about to draw the second time, the sample space looks exactly like this. All the balls are in there. Okay, so the probability the second one is red is the probability I get a red one if I was to draw one time from this. And the answer, bottom number would be 10 and top number is 1. Let me say it one more time. So this has already occurred. Let me change the color here. This has already occurred. That means I've drawn the first ball out of the bag and it was red. Then I put it back in and I'm about to draw the second time. When I go to draw the second time, now I want to know what's the probability that I get a red one so that the second draw is red. And well, what does the sample space look like? It still looks just exactly like this. So what's the probability I get a red out of here? 1 out of 10. This example 5, the problems are kind of too easy. It's a little more interesting when you go to example 6, but I had to put a couple like this anyway. So let's do one more like this. Okay. So again, when you're drawing more than once, I want you to pretend the first draw has already occurred. So this has already occurred. And I want to know what's the probability that I get this on the second draw. So just like the last problem, the idea is the first ball I drew was blue. Okay, that's great. But then we put it back in since we're drawing with replacement before we go to draw the second one. So when I go draw the second one, what does the sample space look like? The new S is the same as the old S. It's this. Nothing has changed because after we draw the first ball, we put it right back in. So I put it back in. Imagine I've drawn the first one, I put it back in, and I'm about to draw again. What's the probability I get a green? And the answer is 3 greens, 10 total. Yeah, that's it for that one. Again, I know it's a little too easy, but you'll understand the difference when we get to example 6. Okay, we got one more question. Are the events R2 and B1 independent? Okay, there's two ways to do this problem. One way to do it is to just say, yes, they're independent because we're drawing with replacements. Let's write that down. So yes, because we're drawing with replacements. Okay, so with replacements, they're always going to be independent. Any two events you give me, they're going to be independent. Okay, so that's one way to say it. And that's fine. I'll take that answer if that's what you write. But let me go ahead and try to write it another way. Let me go ahead and erase this real quick. Okay, so another way to do it is with the formula for independence. So how would it go? So we're going to do a conditional probability here and a regular probability here, and I want to know if they're equal. So you're going to put one of these events, R2 or B1, here in the first slot and B1 and the other one in the second slot. It doesn't matter which one you put where. I'm going to go ahead and put the R2 here. I'm going to go ahead and put the B1 here. So we're going to do R2 given B1. But then once you've determined what goes there, you have only one choice for this. Okay, so one choice. And what is it going to be? It's going to be R2, whatever you have written before the vertical line there. Okay, so over here we're going to put R2. And what you can do is you're going to calculate these two probabilities, and if they're equal, then the events are independent. Okay, so let's see what they are. Let's start with the one on the left. Okay, so this one here. Again, the story is B1 has already occurred, and I'm about to draw a second time. So again, when you're drawing more than once, think about it like this. The event after the vertical line has occurred. That means you've drawn the first one. It's blue. And you're about to draw the second one. So you haven't drawn the second one yet, but you're about to. I don't want to know what's the probability the second one is red. And remember that if this has occurred, the first one's blue, it came out of the bag, but then it goes back in before you draw the second one. So when you go to draw the second one, what happens to the sample space? Sample space stays just like this. So since it stays just like that, what's the probability the second one's red? Well, we've got one red, 10 total in the bag. That's how that one goes. Okay, and then the second question, or the second probability here says, what's the probability you draw red the second time? And irrelevant of what happened the first time, and you already realized that it is irrelevant what happened the first time anyway, because you put it back in. This is also 1 out of 10. You can see they're equal. So they are equal, so R2 and B1 are independent. Some of that might have been so easy that it's confusing, and again, I get that. But you'll see how it changes completely when we get to example 6. All right, let's look at that now. Okay, so once again, we're drawing two balls out of the bag, but this time it's without replacements. So things get more interesting here. And again, I'm asking you to find all these conditional probabilities. So let's go ahead and find the first one. This one says, what's the probability the second ball you draw is red given the first one you draw is red? Okay, so again, remember how we're going to think about this when you draw more than once. This has occurred. That means the first ball we drew was red. And I now want to know if I go to draw the second time, what's the probability the second one is red? So where are we in the process of drawing? The first one's been drawn, and we're about to draw again. Okay, so you need to think of what the new sample space looks like. Okay, so if the first one is red, so if the first ball we drew is red, we're drawing without replacement. That means once we've drawn it, it stays out. We don't put it back in. So if we don't put it back in, then what does the new sample space look like? Well, this says the first one was red. That happened. And it's out of the bag. So it's kind of like this one is gone. And now I'm about to draw from this new bag here. Okay, so this is my new sample space right here, everything else. Okay, so if that's my sample space, what's the probability the second one, the one I'm about to draw, is red? Well, there's no reds left. So it's going to be 0 out of what? Well, how many things are there total? 9. 0 out of 9, which is 0. That should make sense. If the first one was drawn red, what's the probability you get a red again? You can't because there was only one red and it's already been taken out, not going back in, so the probability is 0. So again, did you see how the sample space got changed? In the last problem, it didn't get changed because we put the ball right back in, so we're drawing from the same exact bag again. But this time, one of the balls is out and not coming back in, so the sample space went from 10 things to 9 things. All right, let's go ahead and look at the next one. Okay, so again, whatever's after the vertical line has occurred. So think of it like this. We've drawn the first ball and we're about to draw the second one. So we've drawn the first one, it's blue. It's out of the bag and it's staying out. And I'm about to draw the second one, what's the probability the second one is green? Okay, before I figure out this answer, I want to think of what the new sample space would look like. So I've already drawn the first ball, it was blue. and it's out of the bag and it's staying out. So we got to take a blue one out of the bag. Just take any one that's blue. I guess it doesn't really matter what the number is. Let's go ahead and just cross off this one. That one is out of the bag and it's staying out. And now I'm drawing from this new bag that has 9 balls in it instead of 10. What's the probability I now get a green? Okay, so once you realize what the new sample space looks like, should not be a problem. Bottom number is going to be 9 because again there's 9 things in there. And how many of them are green? 3. So that's just 3 out of 9. You could simplify that if you want, or write as a decimal or something. It's up to you. Okay, let's try the next one. Okay, so this says find the probability that the second ball you draw is blue given that the first ball you drew was blue. Once again, where are we? We've drawn the first one. It was blue. This happened, so it was blue, and it's out of the bag, and we're about to draw the second time. And I want to know, just before I draw the second one, what's the probability I'll get a blue one? So you again have to think, what is the sample space going to look like? Well, we've drawn a blue, and it's out of the bag, and it's staying out. So again, you could just take one of the blues and cross it out because it's been taken out of the bag. Let's just go ahead and cross out this one, for example. Doesn't matter. And everything else now is my new bag, new sample space that has 9 things in it now. And if I draw from this new bag, what's the probability I get a blue? I want to know what is the probability I get a blue. All right, so fraction line, bottom number, 9, because there's 9 things in my new sample space. And how many of those are blue? 3. So answer is 3 out of 9. Once again, simplify if you want, it's up to you. But I'm worried about this example. Some people might write 4 because there were 4 blue ones, but remember we removed 1. So the new sample space doesn't have 4 anymore, it has 3. Okay, so 3 blues left, 9 total left. Okay, let's try the next one. Okay, so this problem is asking, what's the probability the second ball you draw is red, given the first ball you drew is yellow? One more time, let me say where we are in the drawing process. We're about to draw the second one. We've drawn the first, we're about to draw the second one. A little more. We've drawn the first one, and it's yellow. It's out of the bag, and it's staying out. And now I want to know what's the probability the next one is red. So the first thing you do is you figure out what your new sample space is going to look like. If the first one has been drawn and it's yellow and it's out of the bag and it's staying out, then I'm just going to go take a yellow one and cross it out of the bag and see what's left in the bag. Let's go ahead and cross off the 2, for example. It doesn't matter. Any yellow one is fine. So imagine this one is the one that was drawn out and it's gone. It's not coming back in the bag. And now I'm drawing from this new sample space right here. And from this new sample space, what's the probability I get a red? That's the question. Okay, so fraction line. The bottom is going to be 9 because there's 9 things total in the bag. And how many of them are red? 1 red. So that's the answer to that, 1 out of 9. All right, that's how that goes. Okay, a couple more examples. Let's go ahead and look at example 7. Okay. In this example, the experiment's changing. Now we're drawing a card from a poker deck. We're drawing 1 card from a poker deck. And it's asking to find a few conditional probabilities. We're drawing 1, so it's going to go back to the ideas we talked about in class. So when you draw 1 versus when you draw more than 1, remember, you're going to think about conditional probabilities in a little bit of a different way. So when we're drawing more than 1, I told you have to imagine you're at the point to where you're about to draw the second. You've drawn the first already, you're about to draw the second. When you draw only 1, what I want you to think about is that you've drawn it, but you're not looking at it, and someone else is going to give you information about it. Okay, so let's go ahead and look at these examples here. Okay, so in this problem, they're asking you to find the probability of C given A. C is that you get a red face card, and A is that you draw a heart. So I want to think of what happens to the sample space. I'm only drawing 1, so imagine I have a deck of cards. I draw 1 card, I don't look at it, but I show you. And you tell me that A occurred. That means you tell me I drew a heart. As soon as you told me that I drew a heart, we have a new sample space. The new sample space is all the hearts. Ace hearts, 2 hearts. Since I'm running out of room, let me just go ahead and write it like this, King of hearts. Once you told me that I drew a heart, it has to be one of these cards. Can't be anything else. So I automatically know that my sample space that I'm drawing from has 13 things total, so that's what goes in the bottom. And now I want to know what the probability is to get a red face card. So what you want to do is you want to count the red face cards. Red face cards. oops, red face cards that are in here. Okay, that's my whole sample space. Forget about any other cards besides those. And well, all those cards are red. That's good. They're all hearts. How many red face cards are there in this group here? The answer is there's 3. Jack of hearts, queen of hearts, king of hearts are in there. So 3 goes on top. So that's the answer to that one. 3 out of 13. Okay, so let me say it one more time. So we drew one card. I show you. You tell me it's a heart. So now I know there's only one of 13 options it could be. That's why 13 goes on the bottom. Now I want to find the probability that the card is a red face card. So of those 13 in my new sample space, how many of them are red face cards? And there's 3. I didn't list them all here, but it was Jack, Queen, and King of Hearts. Don't put Jack, Queen, and King of Diamonds because they're not in my new sample space. Okay, let's try another one. Okay, this time they're asking to find the probability of B given D. We're only drawing 1, so the way you're going to think about it when you're drawing 1 is like this. So imagine I've drawn 1, I show it to you, but I don't look at it, but I show it to you, and you tell me that D occurred. That means you told me I drew a king. Okay, so this has occurred, I drew a king. Okay, and then I want to find the probability that it's a black card. Okay, so this is the one I'm trying to find the probability of. Okay, so because you told me it was a king, it can't be any of the 52 cards. It can only be one of the 4 kings. So the new sample space is now the king of clubs, king of diamonds, king of hearts, and king of spades. Has to be a king, and there's only 4 kings in the deck. So that's my new sample space. So don't think about any other cards for the rest of this problem besides those kings. So the bottom number is 4 then, because there's 4 things in there total. And now I want to know how many in here are B, whatever B says, black. So how many of these are black? And the answer is 2 of them. King of spades, king of clubs. So 2 out of 4. If you tell me that I drew a king, there's only 1 of 4 options. If I want to know what's the probability now that I have a black card, well, of the 4 options, 2 of them are black. So 2 out of 4. All right, let's try the next one. All right, same thing. We're drawing 1 card from a deck. It says find the probability of D given C. So again, I've drawn 1 card. It's already been drawn. I'm not going to draw a second one or anything, but I don't look at it, and I show it to you. You tell me that C has occurred. You tell me it's a red face card. As soon as you tell me that, I know what my new sample space is. I know it's got to be a red face card. So it's a Jack of hearts, Queen of hearts, King of hearts. Those are the heart red face cards. And then the Jack of diamonds, Queen of diamonds, King of diamonds. Those are all the red face cards. So I know for sure the bottom number is 6. Okay, so now I want to find the probability of D given this new information. I want to know the probability of drawing a king. Don't count all the kings, only count the kings that are in here because my old sample space is gone. It's just this new sample space. And in my new sample space, there's 2 kings, so 2 goes on top. And the answer is 2 out of 6 for that one. Okay, let's see what the question is over here. Okay, so the question is, are the events A and D independent? So the way we're going to do that is we're going to set up 2 probabilities. So I'm going to put a conditional probability here, and put a regular probability here. In the first probability, you're going to put A somewhere, and you're going to put D somewhere. Let me go ahead and put the A first and the D second. You can put the D first and the A second. I think I'll do it that way as well so you can see what happens. But put one of them first, put one of them second. Once you've decided which one goes first, which one goes second, on the right side here, you have to put whatever you wrote first. So it has to be an A here. If you put a D there, it's not going to work. Okay, so whatever's first here has to match what's in here. Okay, so now we're going to calculate those numbers. If those numbers are the same number, those events are independent. If they're different numbers, the events are not independent. Okay, so let's start with the conditional probability. For the conditional probability, D has occurred. That means I drew the card, I didn't look at it, I showed you, and you said I drew a king. That means the new sample space are the kings. So king of clubs, king of diamonds, king of hearts, king of spades. So there's 4 things in the new sample space. Okay, then I want to know the probability of A. Okay, so I want to know the probability of getting a heart. So I want to count the hearts in here. and that's pretty easy. There's just one heart there. So that is 1 out of 4. Now what about probability of A? This is not a conditional probability. So just find the probability of drawing a heart out of an entire 52 deck of cards. 52 card deck is what I meant to say. So 52 down here. And how many of them are hearts? 13. Turns out those are equal. If it's not obvious, put in the calculator, write as a decimal, you get 0.25 here, and you get 0.25 here. So they are equal. So A and D are independent. Yeah, that's how that one goes. Okay, I'm going to do this one more time where I just switch the order of the two terms that are in the conditional probability. So let me go ahead and erase this real quick. All right. So once again, to find if they're independent, I'm going to put two probabilities. This one here is going to be a conditional probability, and this one's going to be a regular probability. But this time I'm going to put the D here and the A here. Remember, it doesn't matter which one you put where. So I'm going to put the D first and the A there. But if I do it that way, then on this side, what do I have to put here? The answer is I have to put D there. I have to put whatever it says first there. It's going to be a D. All right, I'm expecting the same answer because in the last way we did it, we said that it was independent. So I'm expecting these two numbers to be the same so that I get independent again. And that's what will happen. Let's go ahead and look at this. So for the conditional probability, remember A has occurred. That means you told me, think about it like this. I've drawn one card from a deck and I show you, but I don't look at it and you tell me it's a heart. And that tells me now my new sample space is all the hearts. Ace of hearts, 2 of hearts, all the way up to Jack of hearts, Queen of hearts, King of hearts. All the hearts. So that new sample space has 13 things in it, so the denominator for this is 13. But then I want to know the probability of D, the probability I draw a king from this new sample space. There's only one king in the entire new sample space, so 1 out of 13 for that. Okay, and then the right side, probability of D, what's the probability I draw a king? This is not a conditional probability. It's out of the entire deck. What's the probability I get a king? The bottom number is going to be 52. And how many kings do you have in the deck? 4. So 4 out of 52. Those are equal. If you don't believe me, then you put them in a calculator. Now, of course, I have to find a calculator around here. So let's see, 1 divided by 13, and I'm getting 0.076923. Anyway, more digits than that. And 4 divided by 52, of course, same thing, 0.076923. They are indeed equal. So what does that mean? So A and D are independent. Yeah, that's how that one goes. Okay, let's look at example 8. Okay, a detective is trying to solve a murder case. At the outset of his investigation, he knows that the murderer is one of the 200 people in the following table. So apparently the murderer is either male or female, and either from Montebello or Pico Rivera. I made the table red, incidentally, just so you can get in the mood, the murder mystery mood. Okay, so then we have 3 questions. The first one is, what is the probability that at the outset of the investigation, the murderer is female? Suppose that after further narrowing down the suspects, the investigator has determined that the murderer lives in Pico Rivera. Now what is the probability that the murderer is female? Well, I hope that you can see the distinction between A and B. A is just a regular probability. B is a conditional probability. We have further information, and then asks you to find the probability of the same thing. First one says just probably the murder is female. Second one is given this new information, what's the probability the murder is female? So B is a conditional probability. And then for part C, it says are the events murder is female and murder lives in Pico Rivera independent? All right, so look, there's no letters for events mentioned in this question. So the first thing you want to do is you want to make up letters for the different events. There's only 2 events mentioned. One of them is that the murderer is female. So we'll use F for that event. And murder lives in Pico Rivera is the other event. So I think I'll use PR for Pico Rivera for that one. Okay, let's go ahead and write that down first. Okay, so F is going to be the event that the murderer is female. And we'll use PR for the event that the murderer is from Pico Rivera. Okay? Let me make this F a little nicer looking. Still can't make it nice. Okay, that's better. All right, so for the rest of this problem, F is going to stand for the event that the murderer is female, and PR is going to stand for the event that the murderer is from Pico Rivera. Okay, so let's go ahead and answer the questions. Part A, what is the probability that at the outset of the investigation, the murderer is female? Okay, so I'm going to write down the notation for the question first. The mathematical notation for this is just probability that the murderer is female. Okay, it's pretty easy here. You just put a fraction line. We can use absolute value. The classical formula that involves absolute values. It's absolute value of F divided by absolute value of S. And I just count. How many females are there total? Right here, females total 60. 60 goes on top. And how many people total in the entire table? 200. So 60 over 200. Okay, that one was easy enough. The second part is a conditional probability. So suppose after further narrowing down the suspects, the investigator has determined that the murderer is from Pico Rivera. Now what's the probability the murderer is female? The notation now is I want to find the probability the murderer is female, so F goes first. Given the new information, and that new information is that the murderer lives in Pico Rivera. Okay, so once you told me the murderer lives in Pico Rivera, it narrows down my sample space. At the outset of the problem, the sample space was all the people in this table. But it's not anymore because now I have this information, the murder is from Pico Rivera. So my new sample space just gets cut down to the people from Pico Rivera. So everything that's in this green box here, that's my new sample space now. You can ignore all the people that are outside of it. Basically ignore all the Montebello people. Let me do a little bit of erasing here. Okay, so now to get the answer, we're going to put a fraction line here. Well, in my new sample space, how many people are there total? Here's where it says total, so 50 people total in my new sample space, so 50 down here. Okay, and of those, how many are female? So this is the female column right here. So how many female? 15. So that's the conditional probability. Again, you don't go anywhere outside this Pico Rivera column right here. Okay, so that's how that one goes. Again, if you want to simplify it, it's up to you. So this last part says, are the events murder is female and murder lives in Pico Rivera independent? Okay, so to check for independence, we're going to go like this. We're going to do a conditional probability first. Probability, conditional probability, and then regular probability here. Okay, so what am I going to put things? So I'm going to put female either here or here. And I'm going to put Pico Rivera either here or here. So it doesn't matter, but put one of them first, put one of them second. And I'm going to go ahead and put female first and Pico Rivera second because we already found that one. So let me go ahead and erase this now. Oops. Okay, so I'm going to put female here, Pico Rivera here. Then this one has to be female. And of course, we already found all these. So let me go ahead and just put these answers here real quick. So part A was the right side, probably murder is female, which was 60 out of 200. And the right side was part B, probably murder is female given they're from Pico Rivera, was 15 out of 50. And again, if you can't tell if those are equal or not, you put them in the calculator, do it as a decimal, and you're going to get 0.3 here, and you're going to get 0.3 here. Okay, so I wanted to know if they're equal. Now I know. So what's the conclusion? So since I'm running out of room here, let me just go ahead and use the symbols. Murder is female, and murder is from Pico Rivera are independent. They are. Yeah. That's how that one goes. Okay, guys, so practice a lot more conditional probabilities. Get very comfortable with them. And then let's go ahead and just go to the next slide real quick. Because remember, what the story is I want to show you the formulas for a probability of an and. So you need to know conditional probabilities first. So if I assume from this moment on that you're very good at conditional probabilities, then we can look at the and formula. And there's going to be actually two of them, depending on if the events are independent or not. If the events are independent, then to find the probability of an and, you take the probability of each thing and you multiply. Whereas when we were doing the probability of an or, it was the probability of each thing separately and you add. If the events are not independent, then when you find the probability of an and, there's a little more to it. You do the probability of the first times the probability of the second one given the first. Okay, so one thing I want to mention to you is that so the bottom formula can be used all the time, but you want to use the top one if you know the events are independent. If they're independent, what does it mean? It means that probability B given A equals probability B. And if you understand that, then if you look at the second formula here, if you just change probability B given A to probability B, you get this one. So in the case that they're independent, this conditional probability just turns into a regular probability. That's the idea there. Okay, second thing is, when you're doing the probability of an or I'm talking about right now, there's two formulas depending on if the events are what? If you said independent, you didn't hear me. Let me say it one more time. If you're finding the probability of an or, there are two different formulas to choose from. And which one you're going to choose, it depends on if the events are what? Okay, the answer is the events. You want to know if the events are disjoint or not. If they're disjoint, use the short formula. If they're not disjoint, use the longer formula. Now, if we're talking about an and, like this example here, there's a short formula, so we have this one here, and there's a longer formula, this one here. Which one are you going to use? It depends on if the events are independent. Okay, so if the events are independent, use the shorter formula. If they're not independent, use the longer formula. Okay, the only other thing I want to talk about here for just a second is how to remember the formulas. So the top one should be pretty easy to remember. So if the events are independent, when you're trying to find the probability of an and, one more time, let me say it. Saying it in words helps a lot, so you should practice saying it on your own. It's the probability of the first. Don't say probability of A, say probability of the first times probability of the second. And that's the end of the story if the events are independent and you're trying to find the probability of an and. If the events are not independent, you're trying to find the probability of an and. So there's a probability of and. I want you to remember it like this. Probability of the first times probability of the second given the first. Let me say it one more time. To find the probability of an and when the events are not independent, the formula says probability of the first times probability of the second given the first. But that's pretty much all I'm going to say for now because I want to practice those a lot. So we'll practice those next class. Guys, I hope you enjoyed this video. Study super hard and I'll see you in class on Wednesday.